let's get to these last three questions here. This time we are really doing the same thing as 12 and 13, but we're going to plug in a point at the end to find the slope of the tangent line to that graph at that specific point. So once again, we're going to do implicit differentiation. So this first one is just 1 dx. Then we have a minus. And we have to use the product rule in here. So I'm going to put parentheses because that negative gets distributed. And let's go ahead and take the derivative of this. This is going to be a product rule. So we'll have the orange and we'll have the green. So we have first 3, that was orange, 3x. And then derivative of y, or differential of y, is 1 dy. And then we have plus the second, which is y, times the differential of the first, which is the differential of 3x is 3 dx. And then over on the other side, the differential of 4 is just 0. We need to distribute this negative. And we have dx minus 3x dy plus 3y dx is equal to 0. Let's go ahead and add 3x dy to both sides to get, that's the only dy that we have. So we're going to get that to the right side in this case. And over on the left, we can factor out a dx, so we have a 1 plus 3y all times dx equals 3x dy. We want to solve for dy dx, so we're going to divide everything by dx. That cancels the dx, and on the right we'll have dy dx. But at the same time, we can divide both sides by 3x. And so the derivative is 1 plus 3y over 3x. But we want to evaluate this at the point -2, 1. So we're going to put that in there, dy dx, evaluated at -2, 1. We just put the -2 in for x and the 1 in for y. So we have 1 plus 3 times y. Y is the 1 over 3 times x. So 3 times x, which is -2, which gives us an answer of 1 plus 3 is 4 over -6, which reduces to -2/3. And there's our answer for number 14. All right, moving to number 15. Shrink this down a little bit. During the exponential phase, E. coli bacteria in a culture increase in number at a rate proportional to the current population. If the population was 125.9 5.8 minutes ago, so that was 5.8 minutes ago, that was really our starting time. At our starting time, at time 0, it had 125.9 million. And the current population, so after 5.8 minutes, it's 149 million. What will the population be 9.5 minutes from now? All right, so this is a pretty straightforward one because we do have the initial amount. So we can use just our general equation for this a of t. The amount after time t is the initial amount times e to the k t. So this is our later amount. This is after 5.8 minutes. We had 149.0. So in fact, kind of what we have here is we have the 0, 125.9. That's our initial amount. And then we have an amount later on. We have 5.8, 149. And remember, these amounts are in millions. So this is our T and A of T. So that's what we're putting in here, equals our initial amount, which was the 125.9. E to the K times T. That's this 5.8. And then we can solve for K. Well, in order to solve for K, we're going to go ahead and divide both sides by the 125.9. So we have 149 over 125.9 equals E to the 5.8. K. We're going to change this to log form. So this is log base E of the 149 over 125.9 equals 5.8K. Dividing both sides by 5.8. So again, we're going to divide both sides. I guess we can try to write it in here. Whoa, sorry about that. Divide both sides by 5.8 gives us our value of K. So K equals, and this says log base E. We know to write that as natural log of this fraction, 149 over 125.9. Sorry, I wrote that so small. All over the 5.8. So that is the value of K. And then we can go back and we can write this general equation with our value of K in there. So this is A of T equals A of 0, which was the 125.9 times E to the K. K was natural log of 149 over 125.9 over 5.8. I will say, when you get to this step above, you could go ahead and figure out what that equals on your calculator. And that might help instead of writing this whole big thing again as K. So, and then that's K times T. And then you can plug in what you want. It said, what will the population be in 9.5 minutes? That's A of 9.5. And we're going to plug this in 125.9 E to the whatever this weird fraction is. I guess I'll write it out again since I didn't calculate it yet. And then plug in T, which is 9.5. And once you do that, you will get your answer. Which I don't have a calculator with me right now, so you'll just have to find that answer. It is on the answer sheet at the end. All right, and the last question. A supermarket employee wants to construct an open top box from a 16 by 30 inch piece of cardboard. To do this, the employee plans to cut out X by X squares from the four corners so the four sides can be bent upward. write an equation for the volume of the box in terms of x. We'll be seeing these many times, so eventually maybe you won't need a picture. But what's happening here, we have a 30 by 16, cutting out some squares. All these squares are the same size. And once you cut out these squares, you would end up folding up on these orange lines. You would fold everything up, cut out the squares, fold up, and you'll end up with like this little box. So we want to figure out the volume of that box. Well, volume, we're going to have volume in terms of x is length times width times height. Well, we cut out these little x by x squares and folded those up. So these heights are x, and then the length and width are going to be these orange lines. So this orange thicker line here, that's going to be the entire side, which is 30, but we're cutting out two x's. We're cutting out an x here and an x over here. So this orange part is 30 minus 2x. So that's 30 minus 2x. Now we'll go to a different color. This green length here, this whole thing, we said was 16. But again, you're going to be subtracting two x's. So this green part is 16 minus 2x. And that's this 16 minus 2x. So the volume is simply 30 minus 2x times 16 minus 2x times x. Later, you're going to have to multiply these out. I don't think you do for now, but when we get to the problems that we actually solve something with this, we're going to multiply these out. And there you go. Hopefully that